Everything you've ever been told about stillness begins slightly off balance. As a child, you're taught to imagine the sun as calm and unmoving, the Milky Way as a grand wheel turning around a fixed, silent center, a single gravitational pin holding billions of stars in their paths. But when astronomers turned their instruments towards Sagittarius A*, the supermassive black hole at the heart of our galaxy, they uncovered something quietly unsettling. Even this immense core is not perfectly at rest. Careful measurements from NASA's Chandra X-ray Observatory and the Very Large Array revealed minute displacements, not leaps or jolts, but gentle shifts, caused by the gravitational pull of massive nearby stars. The discovery carried a subtle truth: even the deepest center of the Milky Way drifts. Before you sink further into this thought, if you feel inclined to offer a gentle like or softly tap subscribe, I'd be deeply thankful. Each small gesture keeps this quiet corner of the cosmos illuminated and reminds me these calm explorations still find thoughtful listeners like you. Now, let's continue, where the idea of stillness quietly gives way to motion. Part 1: The center that refuses to stand still. For much of modern astronomy, the galaxy's core was treated as immovable, a flawless anchor around which everything else revolved. At that core lies Sagittarius A*, a black hole with a mass roughly 4 million times that of the Sun. It was believed to be fixed in place, the one point in the Milky Way that never wandered while stars and gas traced their endless orbits. Then, in the early years of the 21st century, astronomers began to notice something unexpected. The galactic center, the object that should have remained perfectly still, was subtly shifting. The first clues emerged from the Very Large Array in New Mexico. Night after night, radio signals from the galaxy's core were compared against earlier observations. They were expected to line up exactly. Instead, each year showed a minute offset, only tens of microarc seconds, far too small for human vision, yet unmistakable to precision instruments. It was like observing a mountain creep forward one atom at a time. At first, doubt took hold. Perhaps the instruments were misaligned. Maybe the calibration was flawed. But the same pattern appeared again and again, confirmed by independent observatories across the world. Slowly, an unsettling realization settled in. Even the galaxy's heart quivers. NASA's Chandra X-ray Observatory soon reinforced the finding. Floating above Earth's atmosphere, its detectors captured faint X-rays from superheated matter spiraling near the black hole. Within that glow, scientists noticed gentle, repeating variations, not chaotic, but steady, almost rhythmic. The timing matched the gravitational influence of nearby stars such as S2, S29, and S62, massive bodies racing through space at speeds exceeding 5,000 kilometers per second. As they swept past, each star tugged ever so slightly, pulling the black hole first one way, then another. The result was a delicate cosmic sway, measurable yet profoundly subtle. In 2008, the Max Planck Institute for Extraterrestrial Physics began an observation campaign that would span decades. Using infrared interferometry, Reinhard Genzel and his team traced the motion of those same stars with extraordinary precision. They noticed that when star S2 made its closest approach, the apparent position of Sagittarius A* shifted, not randomly, but exactly as gravity demanded. Years later, Genzel would receive the Nobel Prize for demonstrating that the Milky Way's hidden core was truly a black hole. Yet for him, the fact that this enormous mass could subtly move was perhaps the most haunting insight of all. He once reflected that it felt like listening to the galaxy's own heartbeat. Every data point carried the weight of patience. Chandra's teams had to align mirrors so precisely that vibrations from distant traffic could spoil an entire observation. At the Very Large Array, engineers endured cold desert nights, clearing dust from antenna joints to eliminate microscopic interference. High in Chile's Atacama Desert, near 5,000 meters above sea level, technicians worked in thin air and bitter cold to keep Alma's 66 dishes perfectly tuned.
All of that effort, months turning into years, years into decades, just to measure a drift smaller than the width of a human hair seen from thousands of kilometers away. A quiet reminder that even the most powerful anchors in the universe are never truly still. That quiet movement changes everything. It tells you that gravity is never isolated, never absolute. Even the most massive presence in the Milky Way responds to what surrounds it. Nearby stars, drifting clouds of gas, hidden concentrations of dark matter, all of them press and pull, together shaping a gentle imbalance. The result is a slow, endless sway, the faintest motion ever detected at the galaxy's core. To uncover something so delicate, astronomers relied on a method of almost unbelievable precision: very long baseline interferometry. Radio telescopes scattered across the planet, from volcanic peaks in Hawaii to deserts in Chile, from frozen Antarctic ice to quiet hills in Spain, were linked into a single virtual instrument. Atomic clocks, accurate to a billionth of a second, kept them synchronized. By comparing the arrival times of radio waves from Sagittarius A*, scientists could pinpoint its position with astonishing accuracy, measuring shifts smaller than a few microarcseconds. It was a triumph of patience and coordination, a calm victory over distance and time itself. And what emerged was a picture not of stillness, but of perpetual motion. Later, ESA's Gaia mission added another layer of understanding. By tracking the motions of more than a billion stars, using distant quasars as reference points, Gaia revealed how the entire Milky Way glides through space. Our galaxy, and its central black hole, travels together at roughly 550 kilometers per second. Even the core is carried along, part of a larger flow. As one astrophysicist gently observed, motion is not something that happens within the universe. It is what the universe is. In 2022, that sense of quiet movement became visible. The Event Horizon Telescope released the first direct image of Sagittarius A star. The glowing ring you saw was not just data, it was collaboration made visible. Hundreds of researchers from dozens of institutions waited for clear skies across the globe at the same moment, captured petabytes of information, and spent years refining a single image. When it finally emerged, scientists described it as soft-edged, restless, alive. Even frozen into a frame, it seemed to breathe. For the first time, humanity glimpsed what had long been inferred: the shimmering light of matter circling a black hole that itself drifts gently through space. Like watching the heart of the galaxy rise and fall. And perhaps the most humbling realization is this: that tiny displacement is enough to remind you that even gravity never reaches perfect balance. No object, no matter how dominant, stands alone. Everything listens. Everything responds. The Milky Way's core does not command in isolation. It participates. So when you look up at the pale ribbon of the Milky Way stretching across the night, you can remember that it is all in motion. The stars, the dust, the planets, the black hole itself. The sun, the earth beneath you, the light entering your eyes, all of it drifting together, bound by the same slow pulse. The most stable place in our galaxy is also quietly alive. And within that gentle movement waits another question. If Sagittarius A* wobbles because of what surrounds it, then what, if anything, keeps it centered at all? That curiosity carries you forward. Part 2. What holds a black hole in place? What could cause something so massive, so dominant, to tremble? Sagittarius A*, weighing roughly 4 million suns, bends light, stretches time, and governs the orbits of billions of stars. And yet, it shifts. This faint gravitational sway stands among the most delicate achievements in astronomy, born from one of the most patient observational efforts ever undertaken. In the early 1990s, a small team at the European Southern Observatory began tracking stars near the galactic center. Back then, Sagittarius A* was only a bright radio source, its true nature uncertain, its boundaries unseen. The goal was simple and profound: watch how stars moved, and let gravity reveal what could not be seen. Among those stars was one known as S2, a hot blue-white giant, about 15 times the mass of the Sun. It races through space at nearly 7,600 kilometers per second, completing a full orbit in just 16 years, a heartbeat on cosmic timescales. Each time S2 swept close to the invisible center, its path bent sharply, like a comet whipped around an unseen fire. In 2002, as it reached its closest approach, telescopes across Earth watched its speed surge. There was no longer any doubt. Something unimaginably dense lay at the center, holding the stars in a grip that only a black hole could explain. And yet, even that grip was not perfectly still. Astronomers reached a turning point when observations revealed that the Milky Way's core was not empty, but dominated by an unseen giant. A supermassive black hole occupied that region. Yet precision did not bring simplicity. As measurements sharpened, an unexpected detail emerged. The black hole was not perfectly anchored. Its position drifted, subtly, as though responding to the stars bound closest to it. To uncover this motion, scientists relied on interferometry, a technique that merges light from multiple telescopes to simulate a mirror far larger than any single instrument. By synchronizing observatories across the globe, including facilities in Chile and Hawaii, astronomers achieved a level of resolution once thought impossible. With a very large telescope interferometer, stellar positions could be tracked to accuracies measured in tens of microarcseconds, fine enough to notice a shift comparable to a coin sliding across the surface of the moon. Each star orbiting the galactic center traced a path through warped spacetime, sketching an invisible map shaped by gravity itself. When those maps were combined, the reference point they circled refused to stay fixed. The black hole at the heart of Sagittarius A* was gently oscillating, responding to the gravitational pull of its stellar companions. This motion was first recognized by researchers such as Andreas Eckart, who described it with careful restraint. The displacement was small, but unmistakable. The cause was not a single star, but many acting together. A dense cluster of roughly 30 to 40 massive stars, each far heavier than our Sun, swirled nearby. Their combined gravity was sufficient to make a black hole weighing 4 million solar masses drift by a fraction of an astronomical unit over long timescales. In human terms, the movement was slow. In cosmic terms, it was profound. Picture a massive buoy floating on a restless sea. Each wave nudges it slightly. No single push dominates, yet motion never fully disappears. The black hole behaves the same way. Its apparent stillness emerges only because countless forces balance one another with extraordinary precision. This revelation depended on some of the most advanced instruments humanity has ever built. At Paranal Observatory, the gravity instrument fused 4 telescopes into a single virtual eye, capable of resolving details thousands of times finer than the Hubble Space Telescope. In 2018, it recorded tiny shifts in the light from the star S2 as it raced past the black hole, a direct confirmation of Einstein's predictions. Hidden within that same data was another signal, the black hole itself shifting in response. Each close passage of S2 caused Sagittarius A* to recoil ever so slightly, tugged by gravity like a dancer adjusting to a partner's step. It marked the first time a supermassive black hole was observed physically responding to an individual star. For the scientists involved, the discovery felt almost intimate, as if the black hole itself had revealed a pulse. Years of work went into verifying that motion. Data from observatories separated by continents were synchronized using atomic clocks accurate to billionths of a second. Adaptive optics systems corrected atmospheric distortion in real time, removing Earth's interference from the measurements. All of it served one purpose: to prove that even the most extreme object in our galaxy does not exist in isolation. S2 was not alone. Other stars, such as S62, plunge even closer. S62 completes an orbit in less than 10 years, reaching speeds close to 8% of the speed of light. During these encounters, gravity tightens its grip, and the black hole's position shifts again, a response predicted by refined versions of Einstein's equations. Each interaction adds a faint but persistent rhythm to the galaxy's core, like a heartbeat too subtle to hear but impossible to ignore. To rule out error, teams compared results across independent instruments and methods. Different telescopes, different skies, different algorithms. The drift remained. The motion was real. What this wobble reveals is not instability, but connection. Gravity links every object to every other, from blazing stars to invisible dark matter. No mass stands apart. What keeps the black hole centered is not immobility, but balance, a vast network of forces pulling equally in all directions. The hardest part of uncovering this truth was patience. Astronomers waited decades to trace complete stellar orbits, resisting the temptation to force conclusions before the evidence matured. When the patterns finally resolved, they revealed not disorder, but harmony, a balance so exact that motion itself becomes the only form of stillness. The idea fits perfectly within the framework laid down by general relativity long before such measurements were possible. A shifting center is not a contradiction. It is exactly how gravity is meant to behave. Far from Earth, stars like S2 carve luminous arcs through curved spacetime, their light stretched and bent as they pass the black hole. In response, Sagittarius A* leans almost imperceptibly toward them, then drifts back again. The movement is tiny, yet its implications echo across the galaxy. Nothing remains fixed because everything is connected. And this leads to a deeper question. If even the heart of our galaxy is in motion, then what does center truly mean? On galactic scales, the answer lies in the barycenter, the shared balance point created by all mass in the Milky Way. Just as Earth and the Moon orbit a common center hidden beneath Earth's surface, the galaxy itself moves around a gravitational midpoint shaped by stars, gas, dark matter, and more. Sagittarius A* is not the anchor. It is part of the dance. The stillness we perceive is an illusion born from perfect balance, a universe held together not by rigidity, but by motion endlessly countered by motion itself. Measurements from NASA and ESA reveal that the Milky Way is not stationary in space. Relative to the cosmic microwave background, the oldest light in the universe, our galaxy moves at roughly 552 kilometers per second, drifting in the direction of the constellation Leo. That motion carries everything with it: the central black hole, the spiral arms, and every star visible in the night sky. In a single hour, the entire galaxy travels close to 2 million kilometers through space. This journey is not solitary. The Milky Way moves as part of the Local Group, a gravitationally bound collection of more than 50 galaxies, including Andromeda and Triangulum. Together, they follow a shared path shaped by surrounding mass. Even the heart of our galaxy is embedded in this larger flow. There is no absolute rest frame, only layers of motion, each nested within another. Understanding this motion required unprecedented precision. The story began with 2 space observatories designed to measure the universe with extraordinary accuracy. Gaia, operated by the European Space Agency, was tasked with charting the positions and motions of over 1 billion stars. By tracking how these stars shift across the sky over years, Gaia revealed a subtle but consistent pattern. The entire Milky Way is moving toward a region of space influenced by a massive gravitational concentration. At the same time, NASA's WMAP mission, followed later by the Planck satellite, studied the cosmic microwave background, the faint afterglow of the Big Bang. When mapped carefully, this radiation showed a slight temperature imbalance across the sky. One direction appeared marginally warmer, the opposite cooler. This dipole pattern was not intrinsic to the early universe. It was caused by motion. Our galaxy was moving through that ancient light, compressing it in one direction and stretching it in the other. From this asymmetry, scientists calculated both the speed and direction of the Milky Way's motion with remarkable precision. The result matched Gaia's findings. 2 completely different methods, stellar motion and primordial radiation, pointed to the same conclusion. The Milky Way is gliding through space, carried by gravitational forces far larger than itself. Astronomer Brent Tully described this motion not as a fall, but as a flow. The word captures something essential. Galaxies are not isolated objects drifting randomly. They move along gravitational contours shaped by dark matter and cosmic structure. Even the largest systems participate in this slow, coordinated drift. Seen from afar, the Milky Way appears as a rotating disk more than 100,000 light-years wide. At its center lies Sagittarius A*, surrounded by dense star clusters and clouds of gas. But beyond the visible stars extends a vast halo of dark matter, and beyond that, the galaxy itself traces a slow orbit around a shared gravitational balance point within the Local Group. Zooming out further reveals an even deeper hierarchy. The Local Group moves within the Virgo supercluster, which itself belongs to an enormous structure known as Laniakea, spanning hundreds of millions of light-years. Each scale participates in motion, like nested currents within an ocean. Observations using radio interferometry and cosmic velocity surveys confirmed that this motion extends even to the galactic center. While stars orbit Sagittarius A*, the black hole itself shifts slightly relative to the Milky Way's barycenter. The uneven distribution of mass across spiral arms, gas clouds, and dark matter creates a constant gravitational pull that prevents perfect stillness. One striking confirmation came from studies of masers, natural microwave emissions from star-forming regions scattered across the galaxy. By measuring tiny Doppler shifts in these signals, astronomers reconstructed the Milky Way's three-dimensional motion through space. The direction matched earlier findings. The galaxy, its stars, and its central black hole all move together toward the same gravitational convergence. At NASA's Goddard Space Flight Center, researchers compared Gaia's stellar motion data with Planck's cosmic microwave background measurements. The alignment was exact. Independent instruments, different physical signals, the same conclusion. The Milky Way does not sit at rest. Its center is not fixed. It orbits an invisible point of equilibrium shaped by matter spread across millions of light-years. This discovery was not driven by a single observation, but by patience. Decades of data were tested, recalibrated, and cross-checked against cosmic noise. What emerged was not disorder, but coherence. A universe where motion is universal, and stillness is only an illusion created by balance. Carl Sagan once reflected on our position in the cosmos as humble and unremarkable. Yet even that modest place participates in an immense choreography. The galaxy's core shifts. The galaxy itself flows. Entire clusters drift together, suspended within the unseen architecture of spacetime. If the Milky Way's center is not truly central, and if the galaxy itself follows forces beyond its borders, then a deeper question emerges. What structures guide this motion? What invisible framework holds galaxies in formation, like beads arranged along unseen threads? As we look farther outward, our sense of place dissolves. The Milky Way, with all its stars and planets, is not standing still. It is moving, rapidly, toward regions of space shaped by gravity on the largest scales known. When the heart of a galaxy drifts, the idea of a fixed cosmic center begins to fade. And that realization leads forward, toward the deeper mystery of where this motion ultimately leads, and what unseen forces continue to shape the path ahead. No telescope could pierce that region directly. A thick veil of gas and dust from our own galaxy lay in the way, masking what existed beyond. Astronomers gave this obscured band a name, the zone of avoidance, because visible light simply could not pass through it. Yet curiosity does not stop at darkness. Instead of retreating, scientists changed how they looked. By turning to radio waves, infrared vision, and later X-ray observations, they slowly began to see through the haze. What emerged was unexpected. Vast assemblies of galaxies, layered across hundreds of millions of light-years, all drifting in the same direction. Not scattered, not random, moving together, as if guided by a shared gravitational slope. A major turning point arrived in 2014, when astronomer Brent Tully and his team at the University of Hawaii reconstructed the motions of thousands of galaxies using redshift data. Rather than mapping where galaxies sit, they mapped how they move. The result revealed something profound. The so-called Great Attractor was not a single object at all, but one feature within a far larger structure now known as the Laniakea supercluster, a vast cosmic region containing more than 100,000 galaxies. Within this immense landscape, the Milky Way is not central. It is one spiral arm among many, a small thread woven into a far greater gravitational tapestry. Tully described it with elegant simplicity. We are not plunging inward. We are drifting along contours, following the natural shape of gravity itself. To grasp the scale of this motion, pause for a moment. Our solar system circles the Milky Way once every 230 million years. The Milky Way, in turn, moves with the local group around a shared balance point with Andromeda. Together, these galaxies flow toward the Virgo cluster. And even that cluster is not at rest. Each level is carried within another, motion nested inside motion, continuing far beyond the limits of sight. Behind these discoveries lies quiet human persistence. At the European Space Operations Center in Darmstadt, engineers working on Gaia had to account for the spacecraft's own subtle movements while measuring stars thousands of light-years away. Temperature changes, mechanical vibrations, even solar pressure, all of it mattered. Years were spent refining algorithms that could subtract these disturbances, allowing Gaia to track stellar motion with accuracy measured in microarcsecons. When those stellar measurements were compared with the cosmic microwave background mapped by Planck, the alignment was exact. Independent systems, separate methods, one shared result. The Milky Way's trajectory through the universe was no longer theoretical. It was visible in the data. This truth can feel counterintuitive. When you look up at the Milky Way stretching across the night sky, it appears timeless and unmoving. Yet every point of light you see belongs to a galaxy in motion, sliding through space while spacetime itself gently reshapes around it. Even the Sun, steady, familiar, moves along this path, orbiting the galactic center as the galaxy drifts through intergalactic space. There is no fixed direction here. No absolute up or down. Only motion guided by curvature and mass. In 2020, NASA's Cosmic Flows 3 project refined this picture further. By analyzing distances and redshifts for more than 18,000 galaxies, astronomers created a detailed map of cosmic motion. They found that the Milky Way is indeed moving toward Virgo, but with a slight offset, aimed toward an even more massive structure known as the Shapley supercluster. It was as if the pull we had identified was itself being pulled. Gravity leading to greater gravity. A chain without a final link. Neil deGrasse Tyson once reflected that the universe is not only around us, but within us. In the motion of galaxies, that idea becomes literal. Every atom, every star, every system participates in the same slow cosmic flow. Nothing is exempt. Yet this realization opens a deeper question. If entire clusters, including our own, are streaming toward something, what exactly is exerting that influence? Is it a massive assembly of galaxies hidden behind the zone of avoidance? A vast reservoir of dark matter, unseen yet overwhelmingly strong? Or something woven directly into the structure of spacetime itself? Whatever the answer, we are already part of it. The Milky Way does not choose this path. It follows the geometry written by gravity and mass. Every rotation, every drift, every subtle acceleration ties us to the same unfolding motion. Even now, as these words settle, our galaxy has already moved hundreds of kilometers farther along that invisible current. When you begin to imagine the Milky Way not as a fixed spiral of stars, but as a vessel traveling through a gravitational ocean, perspective quietly shifts. Sagittarius A* is not a point of stillness. It is carried along with everything else. And if even galaxies are in motion, then something larger still must be shaping their course. That mystery waits just ahead. Part 5. The Great Attractor. The unseen presence powerful enough to draw thousands of galaxies, including our own, across the universe. This is not metaphor. It is one of the deepest unresolved questions in modern cosmology. NASA once described it as an invisible gravity well etched into the fabric of space itself. Astronomers gave it a name, the Great Attractor. It lies roughly 150 to 250 million light-years away, in the direction of Centaurus and Norma, hidden behind the dense foreground of our own galaxy. For decades, it remained concealed, as if the universe had placed it deliberately behind a curtain of stars. The first clues surfaced in the 1970s, when astronomers began carefully measuring the redshifts of nearby galaxies. According to Hubble's law, galaxies should recede uniformly as the universe expands. But something was wrong. Entire clusters appeared to be moving toward a specific region of space instead. At first, the anomaly was dismissed. Data errors. Statistical noise. But the pattern persisted. By 1986, astronomers Lindenbell and Dressler published results from a massive survey of over 400 galaxies. The conclusion was unavoidable. Something enormous was influencing their motion. Something unseen was pulling. And that discovery marked the beginning of one of cosmology's most enduring mysteries. Their measurements revealed a vast, coordinated movement of matter flowing toward the constellation Centaurus. The unseen influence responsible for this motion was given a name: the Great Attractor. From that moment on, scientists at NASA, ESA, and observatories across the world began an ambitious effort to uncover its nature. The challenge was immediate. This region lies directly behind the dense plain of the Milky Way, where dust and gas overwhelm visible light. Traditional telescopes could not penetrate the veil. So astronomers shifted their approach, listening instead of looking, using radio waves, infrared light, and X-ray signals that could slip through the obscuration. During the 1990s, the Parkes Radio Telescope in Australia launched the H.I. Parkes All-Sky Survey, observing the universe using the 21-centimeter hydrogen line. These radio wavelengths pass freely through interstellar dust. Slowly, patiently, a hidden picture began to form. Beyond the bright band of our own galaxy sat a massive concentration of matter, the Norma cluster, containing thousands of galaxies bound tightly together by gravity. What emerged was astonishing. The Great Attractor was not a single object, nor a solitary cluster, but a vast region of excess mass embedded within the cosmic web. It stretched across hundreds of millions of light-years, filled with galaxies whose combined gravitational pull was strong enough to alter the large-scale flow of cosmic expansion itself. Later, ESA's Gaia mission and NASA's Cosmic Flows program independently confirmed the direction and speed of our motion. The Milky Way, along with nearby galaxies, is moving at nearly 600 kilometers per second toward this immense gravitational basin. And beyond it lies something even more powerful: the Shapley supercluster, an enormous assembly of over 8,000 galaxies, containing a mass equivalent to 10 quadrillion suns. This realization reshaped the mystery. The Great Attractor may not be the ultimate source of the pull, but rather the nearest visible slope of an even deeper gravitational landscape. To describe this motion, scientists borrow language from fluid dynamics. Galaxies do not streak through space like projectiles. They drift, curve, and flow, much like rivers tracing valleys across a landscape shaped by gravity. NASA astrophysicist Yehuda Hoffman expressed it simply: galaxies are not only carried apart by expansion, they are guided along the contours of the cosmic web. In that web, the Great Attractor forms a deep gravitational valley, subtly redirecting space itself. Consider the scale of this journey. Our Sun completes one orbit around the Milky Way every 230 million years. The Milky Way, in turn, drifts toward the Great Attractor over billions of years. Every rotation, every orbit, every slow shift we make is part of this ancient current, a gravitational flow that began near the dawn of time. We are not observers standing still. We are travelers, carried quietly by the same force that moves galaxies like leaves along a silent cosmic stream. Mapping this flow required extraordinary care. In 2016, an international team led by Helene Courtois at the University of Lyon analyzed data from the Cosmic Flows 2 survey, measuring the motions of more than 8,000 galaxies in 3 dimensions. Using a mathematical technique known as Wiener filtering, they stripped away random motions to reveal the underlying gravitational pattern. What remained was breathtaking: a map of the local universe showing rivers of galaxies converging toward a single immense basin, Laniakea, our home supercluster. Within it, the Great Attractor appeared as a central node, where countless flow lines meet. Courtois summarized the discovery with quiet wonder. "Our cosmic home," she said, "is far larger than we ever imagined. Behind each of these images lies a story of endurance. Data from dozens of observatories had to be aligned, cross-checked, and corrected for Earth's motion, cosmic expansion, and relativistic effects. Each pixel on the final maps represented thousands of hours of computation. Precision, patience, and restraint shaped every conclusion. And still, the mystery deepens. The farther we look, the more motion reveals itself. When the James Webb Space Telescope turned its infrared vision toward the zone of avoidance, it offered a new glimpse beyond the Milky Way's veil. Using its near-infrared camera, Webb detected faint, distant galaxies, some likely connected to the outer regions of the Great Attractor. Their light had traveled hundreds of millions of years to reach us, yet their motion still aligned with the same gravitational direction. Across every scale, the message is consistent. Our movement through space is not random. When you gaze at the night sky, every star, every galaxy, every particle of light is in motion, drifting, curving, flowing along invisible gravitational contours. The Milky Way is not simply spinning in place. It is traveling across the universe toward a destination we cannot yet see. We are bound to this journey by the same physics that governs atoms, planets, and black holes. Even the most powerful telescopes cannot yet reveal the full structure of the Great Attractor. Its shape must be inferred from the motion of everything it influences. In that sense, it is one of the most elusive structures ever discovered. Not because it hides light, but because it conceals certainty itself. Astronomer René Cronkortweg, one of the pioneers in mapping this region, once reflected that while our eyes remain blind behind the dust, gravity is not. It traces what lies hidden. Gravity connects everything, from the smallest particle to the largest supercluster, guiding the universe's motion without sound or spectacle. It is the one language every object understands. So as we drift toward the Great Attractor, carried gently through the darkness between superclusters, remember this: the Milky Way is only one traveler among many. And what draws us forward is not a monster of matter, but a curvature in spacetime itself, a gravitational basin deeper than imagination. Yet one question remains. If something this vast is pulling us, what lies beyond its reach? Part 6. The Zone of Avoidance, the universe's hidden blind spot. What if one of the greatest mysteries in cosmology is concealed directly behind our own galaxy? For nearly a century, astronomers have known there exists a region of the sky where observation fails, a band so saturated with dust, gas, and starlight that even our most powerful instruments struggle to see through it. This region is known as the Zone of Avoidance, a term that sounds poetic, but describes a very real observational boundary. It spans nearly 1/5 of the entire sky, masking whatever lies beyond. For decades, this blind zone has concealed the true source of the gravitational pull we call the Great Attractor. It is like attempting to map the Earth from space while a permanent storm hides an entire ocean. Astronomers could see galaxies bending toward something massive in the direction of Centaurus, but the source itself remained unseen. As NASA once explained, the Great Attractor sits behind the Milky Way's dust, hidden not by distance, but by our own galaxy's structure. In the early 1980s, optical telescopes were helpless against this barrier. Only radio waves, unaffected by dust, could pass through. Using the 21-centimeter hydrogen signal, astronomers at the Parkes Observatory began patiently scanning the southern sky, assembling faint detections piece by piece. Each signal was a fragment, a clue emerging through fog. By the late 1990s, these radio surveys revealed that the zone was anything but empty. It was crowded with galaxies, densely packed near what we now call the Norma cluster, the hidden heart of the Great Attractor. But even then, the picture was incomplete. And the universe, as always, was waiting for us to look more carefully. As astronomers pushed their observations deeper, they began to understand that the darkness was not merely dust. It was complexity layered upon complexity. The Milky Way itself floods the sky with light, gas emissions, and radiation that overwhelms sensitive instruments. Against this glare, everything beyond becomes uncertain. A vast portion of the universe remained concealed, not empty, but unreadable. That began to shift with a new era of observation. In 2013, the European Space Agency launched Gaia, a mission designed not simply to chart stars, but to measure motion with unprecedented precision. By tracking the positions and velocities of more than 1.5 billion stars, Gaia revealed minute deviations in their paths, subtle bends that hinted at gravitational forces acting from far beyond the visible edge of the galaxy. At the same time, infrared observatories such as NASA's WISE and Spitzer began to pierce the galactic dust. Infrared light, longer in wavelength than visible light, can pass through clouds that would otherwise block our view. These telescopes uncovered galaxies hidden directly behind the Milky Way's plane, objects that had always been there, but never seen. When these datasets were combined, a new picture emerged. Thousands of previously invisible galaxies populate the region behind our galaxy, forming part of the same gravitational architecture that draws the Milky Way toward the Great Attractor. One of the most striking revelations came from the 2-micron all-sky survey, which used near-infrared light to map the concealed sky. Entire galaxy clusters appeared where nothing had been catalogued before. It was as though a curtain had been lifted from a cosmic landscape that had always existed, waiting silently behind the stars. Astronomer René Cron-Korteweg, who devoted decades to studying this hidden region, described the moment with quiet awe. For the first time, she said, we were truly seeing beyond the Milky Way's dust, and what lay there was extraordinary. Yet a problem remained. If the Great Attractor were made only of visible galaxies, their combined mass should account for the gravitational pull we observe. But it did not. Even after counting the newly discovered clusters, the numbers fell short. There simply was not enough ordinary matter to explain the motion of entire superclusters. That realization pointed towards something deeper. In 2022, the James Webb Space Telescope turned its infrared vision toward the zone of avoidance. With wavelengths capable of penetrating even the densest clouds, JWST's near-infrared camera detected faint, distant galaxies whose light had traveled hundreds of millions of years to reach us. Many of these galaxies appeared aligned along vast filaments predicted by cosmological simulations, structures dominated not by stars, but by dark matter. ESA scientists now believe the Great Attractor is not a single object at all. It is part of a sprawling dark matter network woven through the local universe. As one researcher put it, the Great Attractor is not a thing, it is a direction in gravity's flow. To imagine this, picture the universe as an invisible ocean. Galaxies float like vessels upon it, carried by currents they cannot see. We observe only the motion of the boats, not the water beneath them. The zone of avoidance does not hide emptiness, it hides the currents themselves. Behind every breakthrough lies a human story. For more than 30 years, astronomers like Cron-Korteweg and her collaborators examined photographic plates by hand, marking faint smudges near the galactic plane that others ignored. Their work was slow, solitary, and often met with doubt. Yet they persisted, convinced that the hidden sky held the key to cosmic motion. When modern digital surveys finally confirmed their predictions, the moment was deeply moving. The universe, at last, had answered. Today, with Gaia's exquisite astrometry and JWST's unprecedented resolution, that faint whisper has become a clear signal. We now see extended chains of galaxies, long filaments and dense knots, stretching through the zone of avoidance. These structures link the Norma cluster, the Hydra Centaurus region, and the Shapley concentration into a single, immense gravitational network. Our galaxy, it turns out, is not being drawn by one unseen giant, but by an entire lattice of mass, dark matter, gravity, and cosmic flow acting together. And still, the mystery is not complete. Even now, roughly 10% of the sky remains hidden, beyond the reach of infrared instruments. Within those uncharted regions may lie additional superclusters, or perhaps the deepest source of the motion we attribute to the Great Attractor itself. As Neil deGrasse Tyson once observed, the universe is under no obligation to make sense to us. Yet, slowly and patiently, it does, through precision, persistence, and the willingness to look where light itself struggles to go. So tonight, when you imagine the Milky Way as a luminous river arching across the sky, remember that it is also a veil. Behind it lies a vast realm of unseen galaxies and invisible matter shaping the motion of everything we know. The universe is not only expanding, it is pulling, guiding, responding to structures we are only beginning to uncover. And the zone of avoidance, once our greatest blind spot, may soon become our most revealing window. But if dark matter and hidden structures guide our path, then perhaps they are not merely influences. What if the true anchor of our galaxy is not Sagittarius A* at all, but something far larger, woven entirely from matter we cannot see? Part 7. Is dark matter the true anchor of the galaxy? For generations, we imagined the Milky Way as a vast spiral of stars orbiting a single gravitational heart. Yet the deeper astronomers look, the clearer it becomes that this picture is incomplete. Surrounding every visible star, every planet, and even the central black hole itself is a massive, invisible structure that outweighs them all, the dark matter halo. This ghostly framework accounts for nearly 85% of the Milky Way's total mass. Dark matter emits no light, absorbs no radiation, and interacts almost exclusively through gravity. It cannot be seen directly, yet without it, galaxies like ours would tear themselves apart. NASA explains it simply. The stars in a galaxy move far too quickly to remain bound by visible matter alone. Something unseen must be holding everything together. The evidence emerged in the 1970s, when astronomer Vera Rubin measured how stars move at the outskirts of spiral galaxies. Classical physics predicted that stars farther from the center should orbit more slowly, just as outer planets move more gently around the Sun. But that is not what Rubin observed. Across galaxy after galaxy, the outer stars moved just as fast as those near the center, sometimes even faster. No amount of visible matter could explain this behavior. Rubin concluded that each galaxy must be embedded within an enormous halo of unseen mass extending far beyond the luminous disk. "What you see," she later said, "is only the frosting on the cake." Today, scientists estimate that the Milky Way's dark matter halo stretches more than 200,000 light-years across, enveloping the entire galaxy in a sphere of gravity. Its total mass is roughly 1 trillion times that of the Sun, about 10 times greater than all stars, gas, and planets combined. This means that Sagittarius A*, immense as it is not the true anchor of the galaxy. It is only one feature suspended within a much larger invisible structure. Gaia has provided some of the clearest confirmation of this reality. By measuring the three-dimensional motions of billions of stars, the mission has revealed subtle distortions in their orbits, patterns that can only be explained by dark matter's gravitational influence. In 2022, ESA scientists published results showing that the Milky Way is embedded within a vast halo that extends far beyond the visible disk, shaping the motion of every star within it. Even the Sun's journey around the galaxy, moving at about 220 kilometers per second, is governed primarily by this unseen mass. To picture it, imagine the Milky Way not as a solid structure, but as a glowing jellyfish drifting through an invisible ocean of gravity. The deeper astronomers looked, the more they realized the darkness was not merely dust. It was complexity. The Milky Way itself floods the sky with light and radiation. Its stars, gas, and magnetic fields create a luminous fog that blinds instruments trying to peer beyond the galactic plane. What lay behind it remained uncertain, an entire swath of the universe hidden from view, unexplored and unmapped. That began to change with a new generation of telescopes. In 2013, the European Space Agency launched the Gaia mission with an ambition far greater than simply mapping stars. By measuring the precise motion of more than 1.5 billion stars, Gaia could detect subtle distortions in their paths, tiny gravitational fingerprints suggesting that something massive was influencing the Milky Way from far beyond its visible edge. At the same time, infrared observatories such as NASA's WISE and Spitzer telescopes began cutting through the dust. Infrared light, invisible to human eyes, revealed galaxies buried behind the Milky Way's glare, galaxies that optical telescopes had never seen. Together, these observations began to lift the veil. Surveys using near-infrared wavelengths uncovered thousands of hidden galaxies clustered behind the so-called zone of avoidance. Entire galaxy groups and massive structures emerged from the darkness, forming part of a vast gravitational network pulling our galaxy through space. One of the most striking revelations came from the 2-micron all-sky redshift survey, which revealed dense clusters of galaxies directly behind the Milky Way's plane, structures that had existed all along, unseen. As astronomer René Kron-Kortweg, who devoted decades to mapping this hidden sky, once said, "We are finally beginning to see through the Milky Way's dust, and what we find beyond it is extraordinary." Yet even as the picture sharpened, a troubling question remained. If the great attractor were made only of visible galaxies, its mass should be measurable. But the numbers did not add up. The galaxies we could see were not enough to explain the enormous gravitational pull affecting entire superclusters. Something else had to be there. In 2022, the James Webb Space Telescope turned its infrared vision toward the zone of avoidance. Its near-infrared instruments detected faint, ancient galaxies whose light had traveled hundreds of millions of years to reach us. Many appeared aligned along invisible filaments predicted by cosmological simulations, structures dominated not by stars or gas, but by dark matter. The emerging conclusion was profound. The Great Attractor may not be a single object at all. It may be a direction, a flow within a vast dark matter network stretching across the local universe. As one researcher described it, the Great Attractor is not a thing. It is a gradient in gravity itself. Imagine the universe as a vast, invisible ocean. Galaxies are boats upon its surface, carried by currents we cannot see. We do not observe the water, only the motion it causes. That is what the zone of avoidance hides. Not emptiness, but motion. Behind every breakthrough lies human persistence. For decades, astronomers painstakingly examined photographic plates by hand, marking faint smudges near the galactic plane, often in isolation, often dismissed. When modern digital surveys finally confirmed their predictions, it was deeply emotional. The universe had answered back. Today, with Gaia's astrometric precision and JWST's unmatched sensitivity, that whisper has become a signal. We now see long filaments of galaxies threading through the hidden sky, connecting the Norma cluster, the Hydra, Centaurus region, and the Shapley concentration into one vast gravitational lattice. Our galaxy is not being pulled by a single monster. It is being carried by a web. Still, the zone of avoidance remains one of astronomy's final frontiers. Nearly 10% of the sky is still concealed, even from infrared eyes. Within those unseen regions may lie new superclusters, or the deepest source of the motion we attribute to the Great Attractor. As Neil deGrasse Tyson once said, the universe is under no obligation to make sense to you. And yet, slowly, patiently, it does. When you look at the Milky Way stretching across the night sky, remember, it is not only a river of stars. It is also a curtain. And behind it lies a hidden architecture shaping the motion of everything we know. The universe is not just expanding. It is flowing. And the greatest forces guiding that flow may still be invisible. It is a view so vast that even light requires billions of years to cross it. Behind these discoveries lies an extraordinary story of collaboration, patience, and technology. Mapping Laniakea depended on precise measurements of redshift, the stretching of light as galaxies move away from us. Each redshift reveals a velocity, and when thousands of these measurements are combined, they do more than show motion. They reveal direction. They trace the invisible flow lines of gravity across the cosmos. In visualizations produced by NASA and the Institut de Physique du Globe de Paris, these flows ripple and twist through space, converging like ocean currents descending into deep gravitational trenches. This is not random motion. It is choreography, gravity performing across billions of light years. What is most remarkable is the consistency of this movement. Galaxies separated by hundreds of millions of light years still follow coherent paths, like synchronized dancers bound by invisible tension. Large-scale simulations such as Illustris TNG and the Millennium Project reproduce the same patterns, showing that the universe evolves not chaotically, but rhythmically, as if space itself has a pulse. Astronomers sometimes call this the breathing of the universe, a slow expansion and counterbalance shaped by two opposing forces. Where matter gathers, gravity dominates, pulling galaxies inward and forming clusters. In the vast voids between them, dark energy pushes space outward, accelerating expansion. The structure of the universe emerges from this balance, the push and pull of existence itself. As NASA scientist Nita Bakal once wrote, "We live in the balance between gravity's embrace and the universe's breath." To study this balance, researchers use baryon acoustic oscillations, ancient sound waves frozen into the fabric of the early universe. These ripples act as a cosmic ruler, allowing astronomers to measure how space has expanded over time. By comparing them with galaxy surveys, missions like ESA's Euclid and the Dark Energy Spectroscopic Instrument, DESI, are mapping how the cosmic web has stretched and evolved. Their findings may reveal how dark matter and dark energy interact, and whether the universe is expanding faster than expected. Each discovery reinforces a humbling truth. Our galaxy is not still. The Milky Way moves within the Laniakea supercluster, which itself flows through an even larger network of filaments extending across the observable universe. We are drifting through a gravitational sea whose currents are older than any star we know. The idea that the universe flows rather than falls is one of the most elegant insights of modern cosmology. When Brent Tully said, "We are not falling into something. We are flowing," it was not metaphor. It was a literal description of cosmic motion. Our galaxy, our local group, and every visible cluster move along pathways carved by dark matter itself. Within that flow, the Milky Way orbits no single center. It drifts as part of the grand motion of the cosmic web. ESA's Gaia Data Release 3 has now allowed astronomers to trace stellar streams and satellite galaxies with unprecedented precision. Even these smaller motions align with the larger gravitational flow. Every movement, no matter how subtle, fits into the universe's expanding geometry. This realization has humbled even the most experienced scientists. As Carl Sagan once said, "The universe is not required to be in perfect harmony with human ambition." And yet, when its structure is revealed through maps and simulations, harmony is exactly what emerges. Every orbit, every drift, every gravitational ripple, all part of a single cosmic rhythm. So tonight, when you imagine the Milky Way drifting through space, remember, it does not travel alone. It moves within a web that spans the universe, connecting us to every galaxy, every cluster, every point of light you have ever seen. The cosmic web does not merely hold us, it carries us. And yet, even this immense structure raises a deeper question. If galaxies flow through a cosmic ocean, what determines the direction of that flow? What invisible current tells space itself where to move? Part 9. A universe with no center. If everything we know, every star, every galaxy, is moving, then what are we all moving around? It seems like a simple question, but when astronomers tried to answer it, they uncovered one of the most counterintuitive truths in all of physics. The universe has no center, and yet everything moves. For centuries, we imagined the cosmos like a great whirlpool. Stars orbit galactic centers. Galaxies gather into clusters. Clusters drift through filaments. But when scientists measured the universe on its largest scales, they found no central point at all. There is no fixed middle, no anchor. What we call motion in the universe is not a dance around a center. It is the expansion of space itself. This expansion, first described by Edwin Hubble in 1929, follows what we now call the Hubble flow. Every galaxy recedes from every other galaxy, not because they are flying through space, but because space itself is stretching between them. NASA describes it this way: galaxies are not moving through space. Space is moving around the galaxies. Imagine a loaf of raisin bread rising in an oven. As the dough expands, each raisin moves away from every other raisin. Yet no raisin sits at the center. That is what happens in our universe. Expansion occurs everywhere, in all directions, equally. Hubble confirmed this by observing distant galaxies and measuring their redshift. The farther away a galaxy was, the more its light was stretched. This relationship, Hubble's law, revealed that space expands uniformly. There is no edge where it begins and no center where it started. The cosmic microwave background, the faint afterglow of the Big Bang mapped by Kobe, WMAP, and Planck, shows the same pattern. In every direction, the universe looks almost identical. This uniformity tells us there is no special place in space. As Stephen Hawking once said, the universe is expanding, but it isn't expanding into anything. Space does not need an outside. It creates its own geometry as it expands. Picture the surface of an inflating balloon. The galaxies are dots on its surface. As the balloon grows, every dot moves away from every other dot. Yet none lies at the center of the surface itself. That center exists only in a higher dimension, one we cannot access. That is our universe. Expansion without a center. Motion without a destination. With data from Gaia and the James Webb Space Telescope, astronomers have confirmed that the Hubble flow continues smoothly across cosmic scales. Even as gravity gathers galaxies into clusters, the universe's expansion remains uniform on the largest scales. Everything moves. Nothing orbits a center. And yet the universe remains perfectly ordered. The Milky Way, Andromeda, and their neighboring galaxies are moving toward one another. Yet, as a group, they are carried outward by something far larger, the stretching of space itself. That expansion isn't slowing down. It's accelerating. In 1998, two independent teams studying distant Type Ia supernovae discovered that galaxies aren't merely receding, they're speeding up. An unseen force is driving this acceleration. Scientists call it dark energy, a mysterious pressure that appears to make up nearly 70% of the universe's total energy. As NASA describes it, dark energy is simply the name we give to the unknown cause of the universe's accelerating expansion. This means the cosmic web itself is stretching over time. Every filament, every cluster, every vast void is carried along, not toward anything, but away from everything else. Galaxies don't orbit a central point because there is no center. Their motion is built into geometry itself, the curvature of spacetime governed by Einstein's equations. Einstein's general theory of relativity, published in 1915, predicted this reality. Matter tells space how to curve, and curved space tells matter how to move. In a universe filled evenly with matter and energy, the only stable solution is expansion, a stretching of space itself. This wasn't intuition. It was mathematics. The universe doesn't need a center to expand. Every point moves away from every other point, and from any perspective, it appears you are at the center, not because you are special but because space expands equally everywhere. Launched in 2023, the Euclid mission is now mapping billions of galaxies to study how this expansion evolves over time. Its goal is to understand the interplay between dark energy, dark matter, and cosmic structure, and to determine whether the universe will expand forever or whether gravity may someday slow it down. Early data already suggests the expansion is extraordinarily smooth, varying by less than 1 part in 10,000 across observable space. That's precision on a cosmic scale. Behind every map and measurement lies a deeper truth. We are not orbiting a single point. We are participants in a continuous unfolding of spacetime. Our galaxy, our cluster, our supercluster, all are carried along by this quiet expansion. Everywhere you look, galaxies are moving away, not because they're fleeing, but because the space between them is growing. NASA calls this the metric expansion of space. It isn't a wave traveling through the universe. It is the universe. And it means there is no absolute rest, no cosmic stillness. Even the smallest atom exists within this expanding fabric. The rate of this expansion, the Hubble constant, is measured at roughly 73 kilometers per second per megaparsec using space telescopes and about 67 using data from the Planck mission. This discrepancy, known as the Hubble tension, remains one of modern cosmology's greatest puzzles. Solving it may require new physics, or a deeper understanding of dark energy itself. When imagining this expansion, don't picture galaxies racing through empty space. Picture spacetime itself stretching, an invisible tide carrying everything with it: light, matter, gravity. The farther away a galaxy is, the faster it appears to recede. Beyond a certain distance, galaxies move away faster than light, not because they violate physics, but because space itself is expanding faster than light can cross it. There is no edge, no outside, only an unbounded expansion governed by laws that operate the same everywhere. As Carl Sagan once said, we are the universe knowing itself. And what the universe knows best is motion without a center. So tonight, when you imagine the Milky Way drifting through the darkness, remember, it isn't orbiting anything at all. It is part of a grand expansion, a ripple in a fabric that never stops stretching. And perhaps that is the quietest truth of all: the universe doesn't need a center to move. Space itself moves. It stretches, carries, and reshapes everything within it. And if space can move, if it can bend, ripple, and breathe, then what we call motion may simply be the way the universe flows around us. You are already moving. Not around anything, but within everything.